Hi everyone, so today we are going to learn about one of the graph algorithms which is known as Dijkstra algorithm. So what exactly is Dijkstra algorithm? It is an algorithm to find the shortest path from one source node to all other nodes within the graph. It is also known as single source shortest path algorithm. So why do you need to know about this algorithm? So before learning any concept, it's important to understand what are actually its real world applications so that it motivates you to actually explore the concept further, and also it enriches your learning experience, right? So let's just try to evaluate Dijkstra on a simple graph, and then we can know about its real world applications. Suppose this particular graph actually represents countries within Europe, and obviously this is a hypothetical representation. So all the nodes actually represent the countries. So this is Germany, Netherlands, Luxembourg, Italy, and London. And the edges between those nodes actually represent the time taken to travel from one country to another. So suppose you are at a particular location in Germany and you want to reach your destination in Italy. So what is one of the routes that you can follow? You can go via London and reach Italy, right? What will be the time taken in that scenario? That will be what? 3 plus 8, which is 11 hours. Now if you take an alternate route, like let's go via Netherlands and then to Luxembourg, then to Italy, what will be the time taken in that scenario? 4 plus 1 plus 4, which is 9 hours. So as you can see, this time is significantly lesser than this time, right? And this is what Dijkstra helps you find. Dijkstra helps you find the most optimal route from your source location to your destination location. So obviously you can guess from this that one of the most valuable application of Dijkstra is in satellite navigation systems, right? So one of the examples that you might be aware of is GPS. So you might have used Google Maps on your phone, right? So if you enter a destination location, it actually helps you by providing you the shortest possible route from your source location to your destination location, right? So underlying Google Maps also uses something like Dijkstra, but they have made significant modifications over this particular algorithm to actually improve the latency, right? So, but the core concept is still this, right? Another one of the usages of Dijkstra is in the networking domain, right? So you all browse internet, right? The underlying communication in on the internet actually happens in the form of IP packets, right? So to actually achieve the lowest latency possible, the IP packets have to be routed via the shortest cost path. So the routers have to forward the IP packets via the most optimal path possible, right? So underlying they use something called as a link state routing protocol, and this link state routing protocol actually incorporates Dijkstra to find that shortest cost path. Right. So now you understand what the real world applications of Dijkstra are. Let's just jump to an example and understand how Dijkstra actually works. Okay. So let's now try to understand Dijkstra algorithm with an example. So we'll simulate this particular algorithm on this example that I've drawn. Right. So this is a directed graph that I've drawn, and we'll try to simulate this algorithm on this graph. Right. So before we do that, before we proceed with the simulation, we need to understand that Dijkstra actually processes a graph in a greedy fashion, right? So what does that mean basically? So it tries to follow these two steps basically. So first, it will try to select the shortest path vertex, right? And once it has selected that shortest path vertex, it will try to explore all its unprocessed neighbors and try to relax their distances. So we'll understand this term once we are actually proceeding with the simulation. So let's just actually proceed with the simulation, and I hope that these two things will be clear, right? So let's just assume that this is the distance array. Let's call it distance array, right? So this is 1, 2, 3, 4, 5, and 6. So these basically represent your edges, so your vertices, right? So initially, if you are at a source vertex of 1, right, and you want to evaluate the shortest path from this source vertex to all other vertices, right? So if you are already at the source vertex of 1, so the distance from 1 to 1 would be 0, right? And because we haven't actually visited any of the other vertices, we'll initialize their distance as infinity. So now what we try to do is, now we try to visit the shortest path vertex. So what is the shortest path vertex? So 0 is the shortest path vertex because all other are infinity, we haven't visited them, right? So let's just try to visit this particular vertex. So now we visit this vertex and we try to relax all its unprocessed neighbors. Now what does relaxation mean? Now 1 is connected to 2 and 1 is connected to 3, right? So in what distance can we reach 2? We can reach 2 in a distance of 1. So but the already assumed answer is infinity. So we'll relax it. So this is 1, this is 1. Now let's look at 3. This is also infinity, we can relax it as well. Right. So now we have processed all the neighbors of 1. Right. Now we can mark it as processed. Let's just mark it as cross. Okay, so this is processed. Now we'll take the shortest path vertex from the remaining vertices. Right. So which is the one we should take? We should take 2. Right. Now let's try to evaluate and relax all its unprocessed neighbors. Right. Now look at 4. Right. So the distance to 4 is actually infinity. But what can be the distance if we go via 2? So that will be what? 1 plus 1. So distance of 2 plus 1, which is what? 2. Right. So what is the other neighboring vertex? Neighbor of 2? It is what? 5. Right. So now we can reach 5. The already assumed answer is infinity. We can reach 5 by a distance of 2 plus 7, which is what? 8. Right. So now we are done exploring its neighbors. Right. Now let's move towards now another one of the, this is done actually, this is processed. Now let's move towards another shortest path vertex. So the remaining vertices are this, what is the shortest path vertex? So this is 4, right? Now let's try to relax all its unprocessed neighbors. The unprocessed neighbors are nothing but those that haven't been processed. Right. So let's start with 4. Now we can reach 3 from 4 in a distance of 1, right? So what is the actually cost if we go via the route 4, right? So we can reach 4 from 1 in a distance of 2, which is already here, right? Now we can reach 3 in a distance of what? Distance of 4 plus 1, which is what? 3. So this gets updated. Also we can reach 6 via distance of what? Distance of 4 plus 8, which is what? Distance of 4 is 2 plus 8 is 10, right? So now we are done processing 4. Let's move on to 3 because out of the remaining vertices, this is the one with the shortest path vertex. Now we start exploring 3. Now we can reach to 5 in a distance of what? Distance of 3 plus 3, which is what? 6, which is less than this. So relaxation means you can actually relax its edges if it's less than the already assumed distance, right? So this will be modified to what? 6, right? Now can you visit any other vertex from 3? No, right? So this is also marked as processed, right? Now let's move on to the remaining vertices, and which one should we take? We should take now 5 because this is the shortest path vertex. Now we try to evaluate the shortest path from 5 to its and relax its unprocessed neighbors, right? Now what is the neighbor for 5, which is 6, right? Distance of 5 plus 2, distance of 5 is what? 6 plus 2, which is what? 8. The already assumed distance is 10, so we can relax it. This is what? So this is also marked. Now once you reach 6, you can't actually go to another vertex, so we can mark it as processed as well. So this is your final distance array that you actually receive once you are done processing or simulating a Dijkstra algorithm. So what does this tell you? That the distance from the source node 1 to the vertex 2 is 1, to vertex 3 is 3, to vertex 4 is 2, to vertex 5 is 6, and to vertex 6 is 8. So basically you have evaluated the shortest path or the shortest cost from the source vertex to all its neighboring vertices. Right. So let's just write a pseudocode and try to analyze the time and space complexity for this. Now we've already seen the simulation of Dijkstra on an example graph. Let's now try to understand it in the form of a pseudocode. Now this is language agnostic, so you can implement this in any language that you feel comfortable with. Let's assume that you are given a graph which is G, and W is your set of edges, right? And S is your source vertex, right? So now, first what did we do in the simulation? Now we initialize the distance from source to source as 0 because you are already at the source, right? The distance to all other vertices is infinity because you haven't actually processed those vertices yet, right? So we add all the vertices to an unprocessed container. Let's just call it Q, right? So what are we doing? Till all the vertices are not processed, we are extracting the minimum from that container, and that is nothing but the shortest, visiting the shortest path vertex, the step 1 in the simulation, right? So and then what are we doing? We are following the step 2 in the simulation. For each neighbor of that particular vertex, we are trying to relax their distances. So basically explore and relax, right? D of y is equal to minimum of d of y, or if you go through this particular vertex, d of x plus h from x to y, okay? So we are relaxing its neighbors, right? And then once we are done processing all these vertices, we return the distance, right? So what is the time complexity for this particular pseudocode that we have written, right? So this loop will evaluate till let's assume that our graph is actually v edges and v vertices and e edges, right? So this particular loop will run till all the vertices are not processed, right? So this will run till v basically, right? Now we'll try to extract min from this particular container. Now let's suppose, like for example, let's just take that this container is an array or a list, right? So the extract minimum from an array, how much time does that take? We have to linearly scan all the elements, right? So in the worst case, that will take up to what time? For each iteration, it will take up to, in the worst case, v time, right? Now what are we doing? We're trying to explore and relax all the neighboring vertices for this particular vertex. So for each vertex, we're trying to explore and relax all its neighboring vertices, right? So if we sum that up for all the vertices, what does that come proportional to? That becomes proportional to the number of edges, which is what e. So this is the time complexity. So this is the time complexity if we take this particular container as an array or a list, right? Now, can we improve upon this time complexity? Yes, we can. How can we do that, right? So currently our bottleneck is where? Our bottleneck is in the extract min operation. So we are taking around, in the worst case, O of v time to extract the minimum element. What can we do in that particular scenario? We can use something like a heap or a height balanced BST, right? So we can use either a heap or a height balanced BST, and if we use either of those, what will be the complexity of extracting the minimum element from either a heap or a height balanced BST? So that will be equal to log of the number of nodes within that particular container. So that will be what? V. So the time complexity will now come down to V into log V plus E. Right? So this sums up basically the time complexity for this particular algorithm. The space complexity is proportional to the number of vertices. The distance is the distance array is has a size of equal to the number of vertices. Also, Q would be the size of number of vertices. So the space complexity is what? O of V. You can write it here. So this is the time complexity, this is the space complexity. And in the next lecture, we can discuss what is the proof of correctness for this particular algorithm. So we will try to prove this particular greedy approach by the form of induction, and we'll also cover some of the shortcomings of this particular algorithm, which is in the case of negative edge weights. Okay, so that is it from today. Thank you.